All right, second part, structural materials and aircraft hardware. I told you all it's going to be a long one, but you know what? We'll get through this. I'll try to make it as quick as possible. But there is a lot of material that's needs to be covered. Also, this upcoming exam is going to be the longest exam. I'm going to make it 100 questions, multiple choice, straight from the ASA general study guide. There's no, there's not going to be no trick questions. It's going to be straight from the study guide. So if you study your SAA, Prepware, and your book, you should be fine. Now, introduction to the second part. The term aircraft hardware describes the various types of fasteners and miscellaneous small items used in the manufacture and repair of aircraft. As an A&P, the importance of aircraft hardware is often overlooked because of its small size. However, the safe and efficient operation of all aircraft depends on the correct selection and use of aircraft hardware. In today's world, there are more than 30,000 different fasteners available for aerospace applications. For ease of understanding, this week's lecture is going to be broken down into two sections, as you will be able to see. The first section discusses the various types of rivets used in constructions and repairs of aircraft, while the second part will look at various other fasteners available in the aviation industry. I can't cover all 30,000, but I will cover, for the most part, the majority of them. While a number of methods are available for joining metal parts, few are ideal for joining aluminum sheets. The most common technique is joining aluminum sheets is riveting. A rivet is a small metal pin with form head on one end. A rivet is inserted into a drilled hole, and its shank is deformed by hand or pneumatic tool. Rivets create a union at least as strong as the material being joined. I think most of you have already had experience with the rivet gun and rivets, so that's a good thing. This is adding a theoretical framework to your practical work that you've already engaged in the lab. So specifications and standards. Before the Federal Aviation Administration issues type certificate for an aircraft, the manufacturer must demonstrate that the aircraft conforms to all airworthiness requirements. These requirements pertain not only to performance, but also to structural strength and integrity as well. To meet these requirements, each individual aircraft produced from a given design must meet the same standards. To accomplish this, all materials and hardware must be manufactured to a standard of quality. Specifications and standards for aircraft hardware are generally identified by the organization originating them. Some of the most common ones are the ones we're going to be able to see during this lecture this week. So you have the AMS, Aeronautical Material Specification, the AN, Air Force Navy, the AND, which is Air Force Navy Design, the AS, Aeronautical Standard, ASA, American Standards Association, ASTM, American Society for Testing and Materials. MS is the military standard. NAF, Naval Aircraft Factory. NAS, National Aerospace Standard. And SAE, Society of Automotive Engineers. These are the most common ones used. When an MS 20470-AD4-4 rivet is required, specifications have already been written for it and are available to both aircraft manufacturers and rivet producers. These specifications stipulate the materials that need to be used and the rivet dimensions that will withstand or withhold all its integrity in aircraft operations and during flight. By using these specifications and calling for standard hardware, aircraft manufacturers are able to build reproducible aircraft at an economical cost. So making things kind of streamlined, make them kind of the standard in the industry, so you don't have to go and have anything specially made, although there are some circumstances, but for the most part you can order your hardware. Solid shank rivets. The solid shank rivet has been used since sheet metal was first utilized in aircraft and remains the single most commonly used aircraft fastener today. Unlike other types of fasteners, rivets change in dimensions to fit the size of the hole. When a rivet is driven, its cross-sectional area increases along with its bearing and shearing strength. Solid shank rivets are available in variety of materials, head design, and sizes to accommodate different applications and aircraft. And also, when you're working with rivets, it's easy to lose track of rivets, so it's important that you account for all your hardware when you're working on an aircraft. Rivet codes. Rivet codes are given to part codes to indicate their size, head style, and alloy material. Two systems are in use today: the AF Navy or AN system and the military standard 20 systems or MS-20. While there are minor differences between these two systems, both use the same method for describing rivets. As an example, consider the rivet designation AN, Army Navy 470 AD 4-5. Before a rivet is driven, it should be extended beyond the base material at least 1.5 times the rivet's diameter. Once driven, the rivet shank expands to fill the hole, and the bulk tail expands to 1.5 times its original diameter. Once the bulk tail expands to the appropriate diameter, it should extend beyond the base material at least 1/2 the original rivet diameter. Now, if we talk about, let's see if I can manipulate this. So this is the rivet head here, right? This is what they're talking about from here. Okay, so this is your rivet. So this whole dimension here should be 1.5 the rivet size right here, from here to here. Okay, this is the mushroom head right there. Okay. The first component of a rivet part denotes the numbering system used. As discussed, this can either be an AN or an MS-20. The second part of the code is a 3-digit number that describes the style of the rivet head. The most common rivet head styles are the universal head, which is represented by the code 470, and the countersunk head, which is represented by the code 426. Following the head designation is 1 or 2-digit letter code representing the alloy material used for the rivet. These codes will be discussed in detail later in the slides. After the alloy code, the shank diameter is indicated in 1/32 inch increments, and the length is increments of 1/16 inch. Therefore, in the example, the rivet has a diameter of 4/32 inch and 5/16 of an inch long in figure 8-2. So here is where I want you to pause and kind of go back and forth so you can see what we're talking about. This is the designations, okay? This is what they're talking about here. All right, so you need to pause and kind of review this. Take notes. Universal and countersunk rivets diameters are measured in the same way, but their length measure corresponds to their grip strength. So length of the rivet, right? So it's now if it's countersunk, it's counting the entire rivet. Okay. Now if it's not countersunk, it only counts from when it's touching the material or the sheet metal. Okay. It doesn't start up here. Pay attention. Okay. It starts from where it's touching or embracing the sheet. Okay. As mentioned, solid shank rivets are available in 2 standard head styles, universal and countersunk or flush. The AN 470 universal head rivet now replaces all previous protruding head styles such as the AN 430 round, AN 442 flat, AN 455 brazier, and AN 456 modified brazier. AN 426 countersunk rivets were developed to streamline airfoils and permit a smooth flow over an aircraft's wing and control surfaces. There is something called parasitic drag. If you look at the drawing that I'm about to draw here, let's just say that this is your wing. Okay, let's just say that this is your wing, and you have hardware sticking out. Let's just say that your hardware is sticking out big time, right? So as airflow goes through here, you are creating something called parasitic drag. That parasitic drag distorts um, uh, air flight, right? So the characteristic of flight. So you are defeating the purpose of flight if you have parasitic drag. Um, Now, before a countersunk rivet can be installed, the metal must be countersunk or dimpled. So you have to drill first. If this is your sheet metal, right, you have to countersink it in order for the rivet to be able to fall in there. Okay, I hope that makes sense. On the other hand, dimpling is the process that mechanically dents the sheet metal being joined to accommodate the rivet head. Sheet thickness and rivet size determine which method is best suited for the particular application. AN 470, AN 422, it's a flat head. Okay, AN 430, round head. Take notes, please. And here's the 455. An alternative to leaving the rivet head sticking up slightly is to use the Alcoa crown flush rivet. These rivets have a slightly crowned head to allow full contact with the gun set. The rivet to drive these rivets, a mushroom type rivet set is replaced directly on the crown flush head. When the rivet is driven, the gun drives the countersunk head into the countersink while simultaneously completing rivet expansion. This result is fully cold work rivet that needs no micro shaving. In figure 8-5, if a countersunk rivet is set with the rivet head flush with the metal surface, some of the gun set's driven energy is lost. However, if the rivet head is allowed to protrude above the metal, all the gun set's energy hits the head, resulting in a stronger joint. On the top left, we have 100% flat countersunk tension head, followed by a crown flush tension head. And then this one here is the flush countersunk shear head. And the last one over here on this side is the 100% crown flush shear head. Here's your gun set. And this is what we're talking about, the gun set. Okay, without damaging your skin, here's your bucking bar. Okay. The raised head of the crown flush rivet allows greater contact area with the rivet set. This results in a stronger countersunk joint. Now, most aircraft rivets are made of aluminum alloy. The types of alloy is identified by the letter, the rivet code, and by a mark on the rivet head itself. Look at figure 8-7. Head markings indicate the alloy used in the common aircraft rivet. So I want you to pause the video and take notes of this. Now, briefly, we're going to talk about 1100 aluminum. Rivets made of pure aluminum have no identifying marks on their manufacturer head and are designated by the letter A in the rivet code. Since this type of rivet is made commercially pure aluminum, the rivet lacks sufficient strength for structural applications. Instead, 1100 rivets are restricted to non-structural assemblies such as fairings, engine baffles, and furnishings. The 1100 rivet is driven cold, and therefore its shear strength increases slightly as a result of the cold working. Now it's 2117 aluminum alloy. The rivet alloy 2117-T3 is the most widely used for manufacturing and maintenance of modern aircraft. Rivets made of this alloy have a dimple in the center of the head and are made represented by letters AD in the rivet part code. Because AD rivet are some common and require no heat treatment, they are often referred to field rivets. The main advantage for using a 2117-T3 for rivets is its high strength and shock resistance characteristics. The alloy 2117-T3 is classified as a heat-treated aluminum alloy, but does not require a reheat treatment before driving or applying. And then we also have the 2017 aluminum alloy. If you remember chapter 7, the first part of the lecture, 2017 aluminum alloy is extremely hard. Rivets made from this alloy are often referred to as D rivets and are widely used for aircraft construction for many years. However, the introduction of jet engines placed greater demands for structural strength on aircraft because of the thrust they produced and materials and fasteners. In response to this, the aluminum industry modified the 2017 alloy to produce a new version of the 2017 aluminum called crack-free rivet alloy. The minimum shear strength of the older 2017 T31 rivet alloy is 30 ksi, while the new 2017 T3 alloy is 34 ksi. D rivets are identified by a raised dot in the center of their head, and the letter D is rivet code. Because of the D rivets are so hard, they must be heat treated before they can be used. Now, figure 8-8, different rivet alloys produce different shear strength in their driven conditions. You can pause and kind of take a note of this and also note the letter for the different alloys, okay? And you can also take a look at the driven condition. And then the markings, okay? The markings is important as well. Moving on, 2024 aluminum alloy. That's the DD rivet. They are identified by two raised dashes on their head. Like D rivets, DD rivets are also called icebox rivets and must be stored at cool temperature until they are ready to be driven. The length of time the rivets remain soft enough to drive is determined by the storage temperature. For example, if the storage temperature is negative 30 degrees Fahrenheit, the rivets will remain soft enough to drive for 2 weeks. When the DD rivets are driven, their alloy designation becomes 2024 T31. 7050 T73 aluminum alloy, designated as E or Echo, a new and stronger rivet alloy was developed in 1979 called the 7050 T73. The letter E is used to designate this alloy, and the rivet head is marked with a raised circle. 7050 alloy contains zinc as the major alloying ingredient and is precipitation heat treated. This alloy is used by Boeing Airplane Company as a replacement for the 2024 T31 rivets in the manufacture of the 767 wide-body aircraft. Stainless steel, right? Corrosion-resistant steel, F as in Foxtrot. These rivets are used for fastening corrosion-resistant steel sheets in applications such as firewalls, exhaust shrouds. They have no markings on the head. So if you're wondering, like, wait a minute, how do I determine? Like, always look at the package. When you're done, if you have leftover rivets, put them back in the correct package so the next person knows exactly what they're working with and they're not trying to engage in guessing work. Now, Manel, or designated as in Mike, Manel rivets are identified with two recessed dimples in their heads. They are used in place of corrosion-resistant steel rivets when their somewhat lower shear strength is not determined. Special rivets. A rivet in any type of fastener that obtains its clamping action by having one of its ends mechanically upset. Conventional solid shank rivets require access to both ends to be driven. However, special fasteners, often called blind rivets, very, very common, okay, very common in aviation, are installed with access to only one end of the rivet. While considerably more expensive, I would say very much more expensive than solid shank rivets, blind rivets find many applications in today's aircraft industry. There's also pop rivets, but they have a limited use on aircraft. They are never used for structural repairs. However, they are useful for temporarily lining up holes. In addition, some home-built aircraft utilize pop rivets. They are available in flat head, countersunk head, and modified flush heads with standard diameters of 1/8, 5/32, and 3/16 inch. Pop rivets are made from soft aluminum alloy, steel, copper, and Monel. So pop rivets, here's a good example, are frequently used for assembly and non-structural application. They must not be used in areas that are subject to moderate or heavy loads. Here's a good example of a pop rivet. If I was you, I would pause this video and pay attention. Take a quick look, okay? Friction lock rivets, another one that's very common. One early form of blind rivets that was the first to be widely used for aircraft construction and repair was the cherry friction lock rivet. Originally, cherry friction lock rivets were available in two styles: hollow shank, pull through, and self-plugging types. The pull-through type is no longer common. However, self-plugging cherry friction lock rivet is still used for repairing light aircraft. And then cherry friction lock rivets are available in two head styles, universal and 100-degree countersunk. Furthermore, they are usually supplied in three standard diameters: 1/8, 5/32, and 3/16 inch. However, larger size can be specially ordered to the company for sizes up to 5/16. This is something that I do want you to really pause and go over. Okay, both of these drawings you should be familiar with. Hook locks are available in four standard diameters: 1/8, 5/32, 3/16, and 1/4 inch, and come in three different alloy combinations of 556 sleeve with a 2024 pin, and an A286 sleeve with a A86 pin, and a Monel 400 sleeve with an A286 pin. Now, cherry locks, mechanical locks rivets, often called bolt cherry lock, was developed shortly after the hook lock. Like the hook lock, the cherry lock rivet is an improvement over the friction lock rivet because its centered stem is locked into place with a lock ring. Now, the Olympic lock blind fastener are lightweight, mechanically locking spindle type blind rivets. Olympic locks come with a lock ring stowed on the head. As an Olympic lock is installed, the ring slips down the stem and locks the center of the stem to the outer shell. These blind fasteners require a specially designed set of installation tools. Olympic lock rivets are made with three head styles: universal, 100-degree flush, and the 100-degree flush shear. Rivet diameters include the 1/8, 5/32, 3/16 inch, are available in 8 different alloy combinations. As the stem is pulled into the rivet sleeve, a bulb forms on the rivet's blind side, and it begins to clamp the two pieces of metal together and fill the hole. All right, this is another slide that I want you to pause and kind of like look over along with this one. Okay, make sure you are familiar with the Cherry Max. So for the last 3 slides, I want you to really pause and get familiar with these, okay? This is the high shear rivet. This is the lock bolt. Lock bolts are manufactured by several companies and conform to the MS standards. These standards describe the size of the lock bolt head in relation to its shank diameter as well as the alloy used. Lock bolts are used to assemble two materials permanently. They are lightweight and are as strong as standard bolts. High lock bolts are manufactured in several different alloys such as titanium, stainless steel, steel, and aluminum. They possess sufficient strength to withstand bearing and shearing loads and are available with flat and countersunk heads. A conventional high lock has a straight shank with standard threads. Although wrenching lock nuts are usually used, the threads are compatible with standard AN bolts and nuts. To install a high lock, the hole is first drilled with an inference fit. The high lock is then tapped into the hole and a shear lock is installed. An Allen wrench holds the high lock bolt in place while the wrench is used to tighten the shear nut. Once the high lock is installed, the collar is installed and tightened. When the appropriate torque value is obtained, the wrenching device shears off, leaving the collar. So, again, pause the video. Understand how this mechanism works. Along with this slide too, figure 8-17, as you can see, both the shear and tension type lock bolts come in a variety of sizes with multiple head styles. Removal of special fasteners. Special fasteners that are locked into place with a crushable collar are easily removed by splitting the collar with a small cape chisel. After the collar is split, knock away the two halves and tap the fastener from the hole. Fasteners which are not damaged during removal can be reused using new locking collars. The removal techniques of certain special fasteners are basically the same as those used for solid shank rivets. However, in some cases, the manufacturer may recommend that special tools can be used. Threaded rib nuts. Goodrich rib nuts were developed by the BF Goodrich company to attach rubber dicer boots to aircraft wings and tail surfaces. To install rib nuts, a hole is drilled in the skin to accommodate the rib nut. A special cutter is used to cut a small notch in the circumference of the hole. The notch lock the rib nuts into the skin to prevent it from turning when it is used as a nut. The rib nut of the proper grip length is then screwed onto the puller and inserted into the hole with the key aligned with the keyway cut in the hole. When the handle of the puller is squeezed, the hollow shank is the rib nut upsets the grip in the skin. The tool is then unscrewed from the rib nut, leaving a threaded hole that accepts machine screws for attaching the boot. Rib nuts are commonly available with flat heads, 100-degree countersunk heads. Countersunk rib nuts are made with both 0.048 inch and 0.063 inch head thickness, with the thinner head used when it's necessary to install rib nuts in a machine countersunk hole in a thin material. Thread type and fits. Aircraft bolt screws and nuts are threaded either by the AMC or the NC and the NF, UNC, or the UNF series. The difference between the American National Series and the American Standard Unified Series is the American National Series has more threads per inch than the American Standard Unified Series. For example, a 1-inch diameter bolt, the NF thread specifies 14 threads per inch, that hence is the 1-14 NF, while the UNF thread specifies 12 threads per inch, hence will be the 1-112 UNF. Both thread types are designated by the number of times the thread rotates number of turns around the 1-inch length of the given diameter bolt of the or screw. When choosing an AN bolt for specific application, you must know the diameter, length, and grip that's required. Okay, you must be able to understand what they're talking about. The grip starts here and it runs through here. Now, if you're working with materials that are actually, hold on, let me see if I can do this. So if you're working with materials that are actually not as thick, you might end up with something that looks like this, where the two sheet metals will run this length. But notice how you're going to be short right here. Okay, so when you put your nut here, you're going to not have enough. So you have to be mindful of that. Here we have an AN standard steel bolt. AN standard steel bolts, corrosion resistant, will be the first one up top here. The steel bolt So these are all common, okay? Now, special bolts will have some type of specification. The drill thread bolt, okay? So get familiar with these. This is another slide that I'm going to highly encourage you to pause and review. The Tinnerman nut and the turn lock fastener. These are very, very common in today's aviation world. So I would like for you to get familiar. So please pause the video and take a quick look. Cable inspection. When inspecting control cables, pay particular attention to those sections of cable that pass through all these pulleys and all the mechanisms. So what we're talking about too is the areas where they can become very very damaged by use. Okay, so we can have cracks here, you can have cracks over here, right? So you need to be aware and mindful of that. The fork end and the cable eye. Turnbuckles provide a means of adjusting control cables as they age and strength or stretch. Sorry. So you can turn, you can insert a screw here and then turn one way or the other, depending which way you want to go, and it'll tighten. It'll bring the cables closer together. Safety and methods. Because aircraft vibrate during flight, there must be some provisions for safety and locking all fasteners to keep them from vibrating loose. Self-locking nuts are used for vast majority of applications in modern aircraft construction, but there are still places where safety wire or cotter pins are needed. For example, drilled head bolts are often used in vibration-prone areas and safety wired together. When installing safety wire, the wires should pull the bolt head in the direction of tightening. So if this is your bolt, okay, you're going to be making sure that when you apply the safety wire, you're pulling the safety wire in the direction, right? You're pulling the safety wire in the direction that's gonna tighten your bolt, okay? Not the other way around. So if this is your bolt, right, you're not going to be installing your safety wire pulling this way. Why not? Because if you pull this way, right, and let's just say this is one way that I actually checked my work when I first started, is let's just say that it's a flathead. I would use a screwdriver after I safety wired it. I would use a screwdriver and then I would go in the rotating a direction where the bolt will be loosened. Now, if the bolt turns, guess what? Yes, you're wrong. So make sure that when you are doing this, you are tightening your bolt in the direction where it's going to tighten. So you run your safety wire this way. Okay? Righty tighty, lefty loosey. Self-locking nuts should not be used on studs, nor should drilled studs be satisfied with cotter pins, since neither of these safety methods prevents something to come loose, hardware to come loose during vibration. Many bolt heads must be safety wired to keep them from becoming loose in general. So again, see, this is pulling it that way. This is going in the same direction, righty tighty, lefty loosey, right? You want to pull in the direction where it's going to keep it tightened. Now, you see this last one, I would stick a screwdriver here, a flathead screwdriver, and I would try to turn it. And if it turns, you're wrong. All right, turnbuckles and swage cable studs must be satisfied to prevent them from becoming loose. You should pause this, take notes. So a lot of you already did this project, but it's something that you need to get familiar with. Bolt head markings. Metric bolt heads are marked with a set of numbers instead of utilizing symbols or lining groupings. The number marked on the bolt heads indicates the strength of the bolt based on the type of materials used to fabricate the fastener. Typical markings range from 4.6 to 12.9, where a higher number indicates higher bolt strength. The number before the decimal point is the minimum tensile ultimately strength of the bolt, given megapascals or MPAs. Pascals are the metric standards for measurements of stress. In the United States, tensile strength is typically given in pounds per square inch, PSI. A bolt mark with a 9.8 would have a minimum tensile ultimate strength of 900 MPa. The number after the decimal point indicates the ratio between the tensile yield strength and the minimum tensile ultimate strength. In the case of 0.8 is the ratio. Therefore, when the two numbers are multiplied together, 900 times 0.8, the result is the minimum tensile yield of 720 MPAs. By comparison, the following metric bolt compares strength to given SAE bolt 6.8, SAE grade 2 8.8, which is equal to SAE grade 5, and the 10.9 equals to SAE grade 8. Thank you very much. That concludes the second part of this lecture, and I will be uploading more documents to Canvas. I am gonna warn you that this upcoming exam is going to have 100 questions. Please feel free to contact me if you have any questions. Appreciate you all. Have a great week. Take care.